Okay, so get this. We're diving deep into Bigtable today.
Bigtable.
Yeah.
Wow.
We're talking massive data storage.
Huge.
The kind that powers Google Search,
Right.
Google Earth, all that.
Yeah.
And to really get into it, we're going straight to the source,
Oh.
excerpts from the original research paper called Bigtable, a distributed storage system for structured data.
Nice.
So it's like a backstage pass
Like it.
to see how this system works its magic.
It's really quite something.
It really is.
Yeah.
And it's incredible how Bigtable was engineered to handle Google's massive data needs.
Massive.
Yeah.
And it's still flexible.
Right.
And it's high performing.
Yeah. It's mind-blowing.
It is.
It powers everything from Google Analytics to Google Finance.
Yeah.
And you know what's crazy?
Right.
They focused on just a few key goals.
Okay.
Wide applicability,
Mm-hmm.
scalability,
Okay.
high performance,
Got it.
and high availability. So basically they wanted a system that could handle anything thrown at it.
Anything.
Yeah, and do it flawlessly.
Oh, that's a tall order.
It is a tall order.
Yeah.
But, to achieve that, the paper mentions a sparse, distributed, persistent, multidimensional sorted map data model.
That's a mouthful.
That's a mouthful, isn't it?
Yeah.
Honestly,
Yeah.
that sounds pretty intimidating.
Well, let's break it down.
Okay.
Imagine a giant spreadsheet,
Okay.
rows, columns,
Yeah.
and cells holding different types of data.
Okay.
That's essentially what Bigtable's data model is all about.
Okay.
And it makes it surprisingly intuitive.
So most people are already familiar with this.
Exactly.
Okay, that makes it a lot less scary.
Yeah.
And to make it even clearer,
Okay.
the paper uses this example called Webtable.
Oh, yeah.
So they use URLs as row keys
Okay.
and different aspects of web pages as column names
Mm.
and the actual content of those pages within those columns,
Yeah.
like a massive web archive.
It's a giant archive. Yeah.
I'm starting to see how the spreadsheet idea works.
It's quite elegant, isn't it?
It really is.
Yeah.
And they use timestamps to track different versions of the data in each cell.
That's smart.
So if a web page is updated,
Yeah.
Bigtable stores both the old and new versions indexed by the time they were collected.
Wow. It's like a time machine for data.
It is like a built-in time machine for your data.
That's really cool.
Isn't it?
Yeah.
But they're talking about petabytes of data across thousands of servers.
Thousands.
So how do they keep this spreadsheet from becoming a monster?
Well, that's where those concepts of rows, columns, and time come together
Okay.
to create a truly scalable system.
Okay.
So rows, for instance, can be any string,
All right.
and they're stored in lexicographical order,
Lexicographical order.
which means they're arranged alphabetically.
Okay, so like A to Z.
Exactly.
Gotcha.
But the real magic is that these rows are divided into tablets.
Tablets.
Yeah, think of them like chapters in a giant book, which are spread across multiple servers.
So it's like breaking that giant spreadsheet into smaller, more manageable volumes?
That's the idea.
Okay.
And then you have column families,
Column family.
essentially groups of columns that share certain characteristics.
Okay.
So in our web table example,
Yeah.
you might have one column family for storing page content
Okay.
and another one for metadata like language or links.
Gotcha.
This structure is super flexible too.
Okay.
You can have unlimited columns within each family.
So you can store tons of data about each row.
Exactly.
So it's about grouping related information together.
Yeah,
Kind of like organizing your files into folders.
exactly.
But how do those timestamps we talked about earlier fit into this whole scalability puzzle?
Well, timestamps are critical for managing different versions of data efficiently.
Oh, wow.
So imagine a website going through multiple revisions
Okay.
with timestamps.
Yeah.
Bigtable keeps track of each version,
Uh-huh.
letting you access any point in its history.
Wow. So with all that data accumulating,
Yeah.
doesn't it get unwieldy?
Well, that's where Bigtable's garbage collection features come in.
Okay, garbage collection.
Yeah, you can actually configure it to automatically delete older versions
Yeah.
based on a number of versions or a time frame.
So it's constantly cleaning house and staying efficient.
It's like a self-cleaning oven for your data.
I love that. A self-cleaning oven for your data.
That's a good analogy.
It is.
Yeah.
So it's this combination of features.
Yeah.
How rows are partitioned, column families are organized,
Right.
and timestamps are utilized.
Exactly.
That makes Bigtable capable of handling truly massive amounts of data.
Massive.
Yeah.
Truly massive.
And these seemingly simple concepts are the foundation for powering some of Google's largest applications. It's incredible.
It is.
So we've got the data model down,
They do.
but a data model is just the blueprint, right?
Right.
How do developers actually work with this data?
Well, you can't just open up a giant spreadsheet on your computer.
Right, exactly.
That's where the Bigtable API comes in.
The API.
Yeah, think of it as the language developers use to communicate with Bigtable.
Okay.
It provides a set of functions for doing things like creating tables, writing data,
Gotcha.
reading data, even deleting data.
So it's the toolkit that they use to actually build stuff on top of Bigtable.
That's a good way to put it, yeah.
Can we see this API in action?
Absolutely.
Oh, perfect.
The paper includes code snippets that illustrate this beautifully.
Okay.
They show how to use the row mutation abstraction to...
Row mutation.
Yeah, for example, add a new link to a web page in the web table.
Okay.
And simultaneously delete an old one, all in a single, unbreakable operation.
So even with complex actions, the API aims to keep things straightforward for developers.
That's the goal.
That's good.
Yeah, keep it simple.
And it goes beyond the basics.
Oh, yeah.
The API includes features like single row transactions, which ensure a series of operations on a single row are treated as one unbreakable unit.
Right. Critical for data consistency.
So it's like making sure a bank transfer completes fully without getting interrupted halfway through.
Exactly.
That makes a lot of sense.
Yeah.
It's like a safety feature for your data.
You could say that.
And then there are counters.
Oh, yeah. Counters are useful.
Which allow you to increment or decrement values stored in Bigtable.
Right.
Useful for things like tracking website hits or how many times an item's been purchased.
Exactly.
So it sounds like they packed a ton of functionality into this API.
They did.
But I'm curious about another piece of this puzzle.
Okay.
How does Bigtable actually store and manage all this data on a physical level?
Well, that's where Google's infrastructure muscle comes in.
Okay.
Bigtable leans heavily on other Google technologies. Like the Google File System, GFS. Stable.
And Chubby.
Okay, hold on. Let's break those down one by one.
Okay.
First, GFS. What's its role? Well, think of GFS as the bedrock upon which Bigtable builds its storage system.
Okay, the bedrock.
Yeah. It's used to store all of Bigtable's log files and data files.
Gotcha.
Spreading them across a vast network of servers.
Okay, so it's the foundation of the whole thing.
The foundation, yeah.
And what about S-Stable?
S-Stable, what's special about that?
Well, S-Stable is Google's own file format, specifically for storing huge amounts of sorted key-value data.
So it's a perfect fit for Bigtable's data model.
A perfect fit.
Allowing for efficient access even with massive data sets.
Exactly.
So think of it like a perfectly organized filing cabinet.
I like that analogy.
Everything is in its place.
Yeah.
Making it super fast to find what you need.
Super fast.
So it's a tailor-made solution for Bigtable's unique way of handling data.
You got it.
And lastly, we have Chubby.
Chubby.
What does that bring to the party?
Well, Chubby is Google's lock service.
Lock service.
And it's more crucial than it might sound.
Okay.
It ensures consistency and reliability in a system as vast and complex as Bigtable. Okay, so for example,
Chubby is used to elect a single master server to coordinate tasks within the Bigtable cluster, preventing conflicts and keeping everything running smoothly.
So it's like having a referee to make sure everyone plays by the rules.
Good analogy.
It's fascinating how these different technologies work together to create a system that's both incredibly powerful and remarkably reliable.
Yeah, it's a real testament to the engineering prowess of Google.
It really is a marvel of engineering.
It is.
But it also sounds incredibly complex.
It is complex.
How do they keep all of these moving parts organized and efficient?
Well, that brings us to Bigtable's ingenious architecture.
Okay.
Which they describe as a three-tier system.
A three-tier system.
Yeah.
Okay, so we'll just dive into that after a quick tour.
That's good.
Okay, back to Bigtable's architecture.
All right.
You mentioned a three-tier system.
Yes.
What's the big idea behind that?
Well, it's all about distributing responsibility and optimizing for performance. The three key players are the client library, the master server, and the tablet servers.
All right, let's unpack those roles.
Okay.
First up, the client library. What exactly does it do?
Well, the client library is the interface that lets developers interact with Bigtable.
Okay.
It's the code that integrates into their applications
Okay.
and gives them access to those API functions we talked about earlier.
Got it. So it's the bridge between the developer's code and the actual Bigtable system.
That's right.
Now, what about the master server?
Master server.
Yeah, what's its role in this three-tiered system?
Think of the master server as the brain of the operation.
Okay, the brain.
Yeah. It handles high-level tasks like assigning tablets to specific tablet servers,
Okay.
detecting when servers join or leave the cluster, and balancing the workload to ensure everything runs smoothly.
It's like the conductor of an orchestra.
Yeah.
Making sure everyone is in sync and playing their part.
That's a great analogy.
And then we have the tablet servers.
Yes, the tablet servers.
Which are like the workhorses of the system.
The workhorses.
Each tablet server manages a set of tablets.
Right.
Handling all the reads and writes for that specific chunk of data.
Exactly.
It's interesting how they've divided the workload. It seems like a really smart way to make sure the system can handle huge amounts of data without getting bogged down.
It is.
But with data spread across so many servers,
Yeah.
how does the system actually find the data it needs?
That's a great question.
It seems like finding a needle in a haystack.
Yeah, it's a challenge.
It is.
But that's where Bigtable's clever tablet location hierarchy comes into play.
Okay, I'm intrigued.
Yeah.
Walk me through this hierarchy and how it helps Bigtable locate data so efficiently.
Well, Bigtable uses a 3-level hierarchy to store tablet location information,
Okay.
much like a B plus tree structure.
A, B plus tree structure.
Yeah, which is a fancy way of saying it's organized for super fast searching.
Okay, super fast searching.
At the top, you have a chubby file that stores the location of the root tablet.
Okay, the root tablet.
Think of this like the main catalog in a library.
Okay.
That tells you where to find different sections.
Got it. So it's like the master index that points you to all the other information.
Exactly.
Okay.
This root tablet then points to all the tablets in a special metadata table.
Metadata table.
Okay. Each entry in this metadata table then points to a set of user tablets.
Okay.
Those are the actual chunks of data you're ultimately looking for.
So it's like going from the main library catalog to a specific sections catalog, then finally to the shelf where your book is.
Exactly like that.
Okay.
But it gets even smarter.
Okay, even smarter.
Yeah, the client library actually caches tablet locations.
Caches the location.
Yeah, so once it knows where a tablet is,
Yeah,
it doesn't have to go through that whole hierarchy again,
gotcha.
making subsequent accesses much faster.
So it's like remembering where you parked your car so you don't have to wander around the parking lot every time.
Exactly.
And to make things even faster, they've added a prefetching mechanism
Oh yeah, prefetching.
where the client library reads metadata for multiple tablets at once,
Right.
anticipating future requests.
Like having a personal shopper.
Oh, I like that.
Yeah,
Gathering everything you need before you even ask for it.
exactly.
Pretty impressive.
It is pretty smart.
But all this distributed data management must come with its own set of challenges.
Of course there are challenges.
How do they handle things like server failures
Yeah.
or keep data consistent across all these machines?
Those are excellent points.
They are.
And Bigtable has some sophisticated mechanisms for tablet assignment and serving that help address those very issues.
Okay, let's dive deeper into those mechanisms.
Right.
How does Bigtable handle the task of assigning tablets to servers and dealing with potential server failures?
Right. Well, it all starts with the master server.
The master server, okay.
Remember, it's in charge of delegating those tablets.
Yeah.
But what happens if a server crashes?
Right.
Well, Bigtable relies on Chubby,
Chubby.
Our trusty lock service to keep tabs on which servers are active and healthy.
So it's like a constant health check
Yeah, a constant health check.
to make sure everything is running smoothly.
That's right.
When a tablet server starts up,
Yeah.
it creates a file in Chubby
Mm.
and grabs an exclusive lock on that file.
Right.
This lock acts like a heartbeat,
Like a heartbeat.
telling the master server, hey, I'm alive and kicking.
Exactly.
If a server loses its lock,
Yeah.
say due to a network issue or crash,
Mm-hmm.
the master server knows to reassign its tablets to a healthy server.
That's how it works.
So it's like a safety net.
It is a safety net.
They make sure data isn't lost even if a server goes down.
Exactly.
And the master server constantly watches that Chubby directory.
It does.
So it can quickly respond to any changes or server failures.
Very quickly.
So it's like a hawk always watching for any signs of trouble.
Always watching.
Pretty impressive. It is.
And once a tablet server is assigned its tablets,
Yes.
it needs to be able to serve them efficiently to client applications.
Of course.
That's where the tablet serving process comes into play.
Tablet serving.
Okay, let's break that down.
All right.
How does a tablet server actually handle requests for data?
Well, each tablet server stores the persistent state of its tablets in GFS.
GFS, okay.
This includes those SS tables
Right.
containing the data itself
Mm-hmm.
and a commit log that keeps track of all the changes.
So it's like having a backup system in case something happens to the server's memory.
Yes, one way to think about it.
But it's not just about persistence. It's also about performance
Right.
to speed things up.
Yeah.
Each tablet server keeps some of its data in memory
Yeah.
in a structure called a mem table.
The mem table.
When a read request comes in, the server checks the mem table first.
Right.
If the data isn't there,
Yeah.
it goes to the SS tables stored on GFS.
That's right.
So it's like having a quick access drawer for frequently used items.
Yeah.
And then going to the storage room for less frequent items.
That's a good analogy.
This combination allows Bigtable to achieve both high performance and high capacity.
That's right.
But you're probably thinking, with all those write operations happening.
Yes. Lots of write operations.
Wouldn't that mem table fill up quickly?
That's a good question. And that's where compactions come into play.
Compactions.
Yeah. Acting like a cleanup crew for Bigtable.
Okay. Tell me more about these compactions and why they're so important.
Well, as write operations happen, the mem table grows.
Okay.
When it hits a certain limit, a minor compaction kicks in.
Minor compaction.
Imagine it like cleaning out your closet when it gets too full.
Okay, I can visualize that.
You reorganize and make space. During this minor compaction, the mem table is frozen.
Frozen?
No more writes allowed.
Okay.
A new mem table is created to handle incoming writes, and the frozen one converts into an SS table and goes to GFS.
So you're essentially archiving older data to make room for new data.
That's a good way to put it.
Okay.
This process has several benefits.
Okay, like what?
Well, it frees up the tablet server's memory.
Okay, that makes sense.
And it also speeds up recovery time if the server crashes.
Oh, okay.
Instead of replaying a massive commit log,
the
server only needs to read the latest SS table.
So it's like having a well-organized filing system that makes it much easier to find what you need.
Exactly.
But over time, wouldn't you end up with a lot of SS table?
Absolutely you would.
Okay.
And that's where merging compactions step in.
Merging compactions.
Periodically, Bigtable merges multiple S tables into one larger SS table.
Okay.
Imagine it like consolidating smaller storage boxes into a bigger one.
That makes sense.
Yeah.
It keeps things organized and prevents the system from becoming too fragmented.
That's the goal.
But what about removing data that's no longer needed?
Good question.
How does Bigtable handle that?
That's where major compactions take center stage.
Major compactions. Okay. A major compaction sounds serious.
It is a bit more involved.
What exactly does that involve?
A major compaction is like a deep clean for your data.
A deep clean.
It rewrites all the S tables for a tablet into a single brand new S table.
Okay. Brand new SS table.
It's the equivalent of taking everything out of your closet, getting rid of anything you don't need, and putting everything back in a neat and organized way.
I like these analogies.
Yeah, they help.
It sounds like a pretty intensive process.
It can be.
But I can see how it would be necessary to keep the system running efficiently.
Absolutely.
A major compaction is especially important because it allows Bigtable to reclaim space previously occupied by deleted data.
That's right.
Remember those delete markers we discussed earlier?
I do.
Well, a major compaction removes them and the data they're attached to, deleting them permanently.
Permanently gone.
It's like hitting empty trash on your computer to get rid of those deleted files for good.
A perfect analogy.
So it's not just about organizing.
No.
It's about actually reclaiming valuable storage space.
Exactly.
But with so much data to process, wouldn't these major compactions take a long time?
They can.
And potentially slow down the system?
That's a valid concern.
It is.
But Bigtable engineers have a clever solution.
What's that?
These compactions happen in the background.
Oh, in the background.
Without interrupting those crucial read or write operations.
So it's like having a cleaning crew that tidies up your house while you're away.
Exactly.
So you never have to deal with the mess.
That's the idea.
That's a fantastic analogy.
Yeah.
It's amazing how they've thought of everything to keep the system running smoothly and efficiently.
They've thought of a lot of things.
But I'm also curious about how all of these technical details translate into real-world benefits.
Okay. Real-world benefits.
Can you give me some concrete examples of how Bigtable's performance enhancements actually impact the user experience in Google's products?
Of course, Bigtable's performance tweaks are not just theoretical.
Well,
they have a direct impact on the speed and responsiveness of those Google services you use every day.
Okay, I'm excited to hear about this.
Yeah.
Let's start with Google Analytics.
Google Analytics.
They rely on Bigtable to store and analyze immense amounts of web traffic data.
Immense amounts.
Yeah.
It's a lot of data.
Okay. I can see how a system like Bigtable would be crucial for a service that handles that much data.
Absolutely. It's essential.
Okay.
Google Analytics uses Bigtable to store raw click data,
Raw click data.
which is information about every visit to a website
Okay.
that uses their tracking code.
So it's like a giant database of all the activity happening on millions of websites.
Millions of websites.
Yeah, it's a mind-boggling amount of data to manage.
It is mind-boggling.
And Bigtable's scalability and performance are essential.
Absolutely.
Imagine trying to analyze billions of website visits using a traditional database system.
Yeah.
It would be incredibly slow and inefficient,
Incredibly slow.
like trying to find a specific grain of sand on a beach.
Great analogy.
So Bigtable essentially makes this massive data analysis possible.
It does.
Bigtable allows Google Analytics to process that vast amount of data quickly,
Very quickly.
providing website owners with those valuable insights without making them wait forever.
That's right.
But Google Analytics is just one example.
One example.
Let's switch gears and talk about Google Earth.
Oh, Google Earth.
I can only imagine the amount of data involved in creating that virtual globe.
It's massive. It's truly massive.
So how does Bigtable actually help Google Earth manage all that data and deliver a smooth experience for users?
Well, they use Bigtable to store all those satellite images
Okay.
and terrain data that make up its virtual world.
Okay, so they use Bigtable to store the raw imagery data,
Right.
as well as process data that's optimized for serving to users.
That's right.
This includes things like different levels of detail for the same image,
Sure.
allowing you to zoom in and out seamlessly without downloading the entire image every time.
That's right.
Think of it like a map that adjusts its level of detail depending on how close you're looking,
Yeah.
showing you street names when you're zoomed in and highways when you're zoomed out.
Exactly.
That makes a lot of sense.
Hmm.
And I can see how Bigtable's ability to handle all that data is crucial for making Google Earth work so well.
It is.
Trying to stream those high-resolution satellite images from a regular database would be like trying to watch a movie over dial-up internet.
I can imagine.
Slow and frustrating.
Very frustrating.
But with Bigtable,
Yes.
Google Earth can deliver all that imagery smoothly,
Smoothly.
letting you explore the world from your computer without any lag.
It's amazing, isn't it?
It's amazing how they've managed to make such a complex and data-intensive application so user-friendly.
Yeah. They've done a great job.
It really is.
Yeah.
And those are just two examples of how Bigtable's performance enhancements have a real-world impact.
Two great examples.
It's impressive how Bigtable can handle everything from analyzing website traffic to powering a virtual globe.
It is.
But I'm curious, what about the people behind Bigtable?
The people behind Bigtable.
What did they learn while building this groundbreaking system?
Well, building a system as vast and complex as Bigtable definitely came with its share of challenges.
Yeah.
They learned a lot.
Okay, I bet.
Yeah.
What were some of the biggest takeaways they gleaned from the Bigtable development experience?
Well, one of the most important lessons was that large distributed systems are susceptible to a much wider range of failures than you might initially think.
Okay.
Wider range of failures than you might expect.
Yeah, it's not just about those common issues like network outages or server crashes.
Right.
They encountered unexpected problems like memory corruption, clock synchronization issues, servers that would freeze up, and even bugs in other systems they were using.
So it sounds like a constant battle against Murphy's Law.
Yes.
Whatever can go wrong will go wrong.
Exactly.
Wow. And this realization forced them to design Bigtable with robustness and resilience at the forefront.
Okay. Robustness and resilience.
Yeah, they anticipated and mitigated as many potential problems as possible.
So for instance,
they added checksumming to their communication protocols to detect and handle data corruption.
So it's like having a built-in safety net.
Yeah, a safety net.
To catch you if something goes wrong.
That's right.
That's reassuring. It sounds like they were always thinking a few steps ahead.
They were always thinking ahead.
To prevent potential disasters.
Always.
They also learned the importance of avoiding over-engineering.
Oh yeah, over-engineering.
Initially, they planned to support very general transactions.
Right.
But they realized most applications only needed single-row transactions.
Right. Much simpler to implement.
So it's about finding that sweet spot between functionality and complexity.
Yeah.
Providing the necessary features without making things overly complicated.
Absolutely.
And another key takeaway was the importance of thorough system monitoring.
Oh yeah, system monitoring is crucial.
They designed Bigtable to collect detailed performance data,
Right.
allowing them to identify and address bottlenecks quickly.
Yeah.
Think of it like a dashboard
Okay, a dashboard.
that gives you a real-time view of how the system is running, you can spot and fix problems before they snowball into major issues.
Exactly.
It's like having a team of mechanics constantly monitoring the engine.
Yeah, I like that.
To make sure everything is running smoothly.
That's a great analogy.
And finally, they really emphasize the value of simple designs.
Simple designs.
Like in the scale of the system.
Yeah.
And the fact that code constantly evolves over time.
Right.
Clear and concise code was essential.
It really was.
For maintainability and debugging.
Yeah.
It's like having a well-organized toolbox.
Yeah.
Everything has its place, making it easier to find what you need and keep things in working order.
A well-organized toolbox is a beautiful thing.
It really is.
Yeah.
These are all incredibly valuable lessons, and not just for those working on systems as massive as Bigtable.
No.
I can see how these principles would apply to any software development project.
Absolutely. These lessons transcend Bigtable's specific context and offer insights into building any complex system effectively.
It's inspiring to see how the Bigtable team not only built this groundbreaking system, but also extracted valuable wisdom from the process, offering guidance for others working on similar challenges.
Exactly, passing on the knowledge.
Well said. We've spent a good amount of time exploring the inner workings of Bigtable.
We have.
But I'm curious about its broader impact.
Broader impact, okay.
How has Bigtable influenced the development of other data storage systems and technologies?
Well, Bigtable's impact is undeniable.
Okay, in what way?
It's not just about the code itself.
Right.
It's the ideas, the architectural patterns, the design philosophies that have inspired countless other systems.
So it's like Bigtable served as a blueprint for a whole new generation of data storage solutions.
Exactly.
Wow.
Its emphasis on scalability, reliability, and simplicity resonated throughout the tech community.
It makes sense.
Yeah, leading to the rise of those NoSQL databases that are so prevalent today.
Can you give me some specific examples of how Bigtable's DNA can be seen in other systems?
Absolutely. Let's look at Apache HBase.
Apache HBase. Okay.
This open source database was directly inspired by Bigtable.
Okay. Wow.
And shares many of its core design principles, such as using a distributed column-oriented data model and prioritizing horizontal scalability.
So it's like HBase took the best ideas from Bigtable and made them accessible to everyone.
That's a good way to put it.
That's fantastic. It's like Bigtable's legacy is being carried forward and expanded upon by these other systems.
Yeah, it's a great legacy.
Are there any other examples?
Of course, consider Cassandra. Another popular NoSQL database. Well, not a direct clone of Bigtable.
Yeah.
It, too, embraces a distributed architecture.
Okay.
And prioritizes scalability and fault tolerance.
So these principles were central to Bigtable's success.
Absolutely.
And have clearly influenced other systems.
Yeah, it's a pattern we see again and again.
It's like Bigtable sparked a movement. A shift away from those traditional relational databases.
Yeah.
Towards more flexible and adaptable solutions.
Exactly.
And this shift was driven by the evolving needs of the tech industry.
Right. As data volumes exploded and applications became more demanding, traditional databases just couldn't keep up.
Right.
Bigtable, with its ability to handle massive data sets and scale horizontally, offered a compelling alternative.
Okay.
It was the right tool at the right time.
It really was.
Perfectly aligned with the needs of a rapidly evolving technological landscape.
It's amazing to see how a system born within Google has had such a profound impact on the world of data storage.
It's pretty amazing.
It is, but its influence doesn't stop with NoSQL databases, right?
No, it doesn't.
What else has it influenced?
Well, cloud storage platforms, like Amazon S3 and Google Cloud Storage, have incorporated many of Bigtable's principles for managing data across a distributed network.
That makes sense.
Yeah. This has enabled them to reliably store and serve colossal amounts of data.
Colossal amount.
It's like Bigtable's ideas have become woven into the very fabric of the cloud.
I like that, woven into the very fabric of the cloud. That's a powerful image.
It is a powerful image.
And has Bigtable had any influence on how we process all this data?
Absolutely. Data processing frameworks. Like Apache Hadoop and Apache Spark. Also draw inspiration from Bigtable's approach to distributed computation. This allows them to process massive data sets in parallel across clusters of commodity servers. Making it possible to extract valuable insights from all that data.
It's mind-blowing to see how Bigtable's legacy has spread to so many different areas of modern data systems.
It really is a testament to the power of good ideas.
So as we wrap up this deep dive into Bigtable, I want to leave our listener with some key takeaways.
All right, key takeaways.
Remember to embrace simplicity.
Simplicity.
Prioritize modularity.
Modularity.
Optimize for data locality.
Data locality.
And never stop iterating and improving your own systems and approaches.
Keep iterating.
And remember, the world of data is vast and constantly evolving.
It is.
Stay curious and never stop exploring.
Never stop exploring.
You never know what groundbreaking innovations might be just around the corner.
That's right.
That's a perfect note to end on.
It is.
Until next time, keep diving deep.